May the 4th be with you. That's right, it's Star Wars Day, May 4th, 2020. Hey, speaking of cool things in space, I happened to be outside last night, about 9 o'clock. I look up at the sky and I can see a satellite going across. And I say, how do you know it's a satellite? One, it's moving, okay? So it's a satellite, it's an airplane, or a bird or something. And I know it's not a bird or something, okay? Satellite, airplane. Airplanes blink. Satellites are a solid point of light, and satellites move across the sky faster, all right? So I see a satellite, that's always kind of cool. And as I'm watching it go across the sky, I see another one coming basically right behind it. As I'm watching, I see another one come. And I watched, as I watched, I saw 9 satellites in a row going across the sky. Each one separated by probably about 10 degrees, okay? Your fist out at arm's length is about 10 degrees. So 9 satellites in a row. Now I had read a couple months back that SpaceX, that's Elon Musk's company, they're putting up a network of satellites for broadband internet use. And their goal is to basically have a network that covers the entire Earth with fast broadband internet. And they're putting up thousands of these mini satellites. They launch them in like a brick of satellites, you know, I don't know how many at a time, but it's at least dozens, if not hundreds. There's this brick of satellites, and they launch this, and then those satellites slowly in orbit separate from each other, spacing themselves out. So eventually, you're going to have all these satellites in orbit around the Earth. And they're small satellites. Each individual one of these is, I think it's a plate, basically, you know, a couple feet across and just kind of thin. But, you know, it leaves this string of satellites. And I had to go back in the house and do some looking up, and it looked like the satellite network is called Starlink, and this appeared to have been from the Starlink 3 launch is what I believe I was seeing based on the time of these satellites going across. So it's kind of cool. Now, let me share the flip side of that. If you're an astronomer going out to look at the sky and study things, you know, we're getting more and more and more man-made objects up there, and it's a little bit like we're littering our nearby neighboring space zone as opposed to the Earth. Now, you know, I have mixed feelings both ways on it. It was cool to see. It really was. It's the first time I had seen that particular network. I hear that after a new launch, and when these satellites are really close together yet, it's a pretty spectacular thing to see in the sky. All right, so enough of that. Hey, again, happy Star Wars Day. You know, maybe I wonder if any of you are dressed up today. You know, any Chewbacca's out there, any Princess Leia, any Han Solo. Oh. Here's our goal for today. We're going to look at our chemical bonding, and we're going to see how atomic orbitals, so this model of how we picture electrons arranged in atoms, how do we blend that to think about electrons arranged in molecules? And so I want you to show some understanding that in chemical bonding, atomic orbitals merge to form something we call molecular orbitals. Okay? This is a little bit of an advanced topic. The lesson's going to be pretty short today. That's okay. I think Wednesday's lesson is going to be a little bit long, so enjoy it today. All right, so a couple of definitions. We're going to talk about sigma bonding, sigma orbitals. In a sigma, and here's the Greek letter, lowercase sigma. You might recognize that an uppercase sigma is that thing we use for like a summation symbol in mathematics, and pi you're certainly familiar with. But sigma bonding refers to an end-to-end overlap of our orbitals, and pi bonding refers to a side-by-side overlap of our orbitals. So let's try this. We're going to look, so here's an s orbital. S orbital is just a spherical region around an atom, okay? And here's another atom with an s orbital. So what's going to happen as these two merge together? We're going to bring these two atoms together, and, well, I need to go over to my mouse to control this better. Hopefully you can still hear me. I'll speak up. So what happens? As we bring these together, these orbitals stretch and merge into one orbital. Now once I've played through that, I can show it kind of as a sped up animation. So they come together and merge. Come together and merge. Now this is not the whole story, because if you think about this, we've got two orbitals. And when I showed you the merge, I was only showing you one shared orbital. So this is saying the electrons are somewhere here, the electrons are somewhere here, and now we're saying that the electrons are somewhere here. But if you merge two orbitals, you get two orbitals. So it turns out what we get is a bonding orbital. So this is a sigma bonding orbital. And then you'd also get a sigma anti-bonding orbital. Now, for what we're doing right now, and we're talking about chemical bonding, the anti-bonding orbitals, for beginning class, I think we can just bypass. All right? But I just want you to understand that if you're merging two orbitals, you're going to get two orbitals. The thing is that what we're talking about usually, remember, most of the time in a covalent bond, you've got an atom that's got one electron in an orbital and one electron in an orbital, and they're coming together to share, so we got two electrons in the bonding orbital. There's no electrons in the anti-bonding orbitals for what we're talking about right now. I'll leave the rest for your college classes. All right, what happens if we have some p orbitals? Okay, well, here's two p orbitals. Remember, p orbital has this peanut shape or dumbbell shape. It's got a region of space with two lobes. And here's a p orbital, two lobes. And sigma bonding is an end-to-end overlap. So we're going to picture these two coming together. And let me just, I better go to my mouse. So we're coming together. It's merging, 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 merging. And here's what we end up with. Looks a little bit like the face of Sid the Sloth from Ice Age. Okay? Now, this is my rendition, trying to do a little animation. I don't promise that it's mathematically accurate. But if we split it apart again, two orbitals, bring them together end to end, and they merge together. So what we're saying is that there's the highest probability of finding the electrons between the atoms. Not individual anymore, but shared together. And there would also be anti-bonding pi orbital. Okay? Now that was the end-to-end. I didn't, for the s orbitals, I didn't try to show a pi bond because you can't really do a pi bond with sigma orbitals. There is only end-to-end. But for p orbitals, we could also look at what if they came together side by side. Okay, so side by side, we're going to move them together. They're going to start to warp together, merge together. Oh. And so we end up with this region of space where, again, kind of roughly between the atoms is where your highest probability of finding electrons are. Split it apart, merge it together. So two individual p orbitals can merge together to form a pi bonding orbital. So pi bonding was the side-by-side overlap. Sigma bonding was the end-to-end overlap. And with s orbitals, there is no difference. If you turn these sideways and bring them together, it's going to look like the same thing. So we only have sigma bonding orbitals with s orbitals. So this is just the last page for today's notes. Trying to keep it short and sweet. So here's just kind of a summary. Two s orbitals merge together to form a molecular orbital. That's a sigma bond. And two p orbitals, sigma bond overlapping end to end, give you something kind of like that. But then two p orbitals overlapping side to side merge together and give you a space kind of like that. Okay? And again, we're talking about this region of space where the electrons are. So it's a little different modeling. Basically, the math, this is the way I understand it, okay? And it may not be a perfect understanding. But we have these mathematical models that come out of quantum mechanics, quantum theory. And math sometimes has multiple solutions. You can just think back to the equation x squared equals 25. What are the answers? You might say, well, x is 5. But x could also be negative 5. There's two answers. Well, let's think about this. Let's say this mathematical model predicts different answers in different situations. So when we have individual atoms, okay, we have s orbitals and p orbitals and d orbitals and f orbitals. But when we have molecules, we have these molecular orbitals where the spaces are joined together. So that's today on molecular orbitals. Again, pretty short today. Longer stuff when we talk about Vesper theory on Wednesday. We won't have Tuesdays from here on out are going to be no additional assignments, sometimes some catch-up things, but no additional assignments. Wednesday we're going to look at Vesper theory, valence shell electron pair repulsion. That's a little more lengthy topic, okay? So enjoy your day. Hope you had a great weekend. Enjoy Star Wars Day. May the 4th be with you.